SwayamPrabha. Digital India. Educated India.
Good morning. Welcome to this course on Introduction to Explosions and Explosion Safety. All of us would have heard of this word explosion. Normally, we associate an explosion with a loud noise, a loud bang, and disruption of things from the place of the explosion. By disruption, I mean things fly out, there is total damage at the place, and therefore all of us are used to connect the word, as we say, explosions with a loud noise, a loud bang, and disruption of things at the place wherein the explosion occurs. In this particular course, we will look at what causes an explosion, what are the different types of explosions, and being disruptive in nature, we will try to see how to mitigate the effect of explosions, and also we will try to see whether we can institute some steps such that we can prevent some of the explosions. Let me start with an example. All of us are aware that maybe in the kitchen we use cooking gas, and very often, maybe at least 3 or 4 times a year, we read in the newspaper some reports that there is a blast due to the leakage of gas from the cylinder containing the cooking gas, or from the stove, or else from the line which conveys the cooking gas into the kitchen. What really happens is, maybe I have a cylinder of gas which is connected to the stove over here. Maybe there is some leakage of gas from the cylinder into the kitchen room. It mixes with air, forms a combustible, and if it finds a accidental spark in the kitchen, like maybe when it is leaking, some mixture is formed, somebody goes and puts on an electrical switch which creates a spark, what happens is you immediately have a loud bang, dum, and then you have the kitchen in shatters. Why the kitchen alone? The entire building which is part of the kitchen is totally demolished. That means an explosion is something which is undesirable, which causes a lot of havoc around you, and this is what we should be studying. This is a simple example, but there are many more examples. Like in the cracker industry, in the fireworks industry, they handle what we call as energetic materials. By energetic materials, we mean materials which gives out some energy. And very often, we find during the processing of these crackers, during processing of these fireworks, we have an explosion. And especially in the state of Tamil Nadu, in the southern belt like Shivakashi, we have a lot of these accidental explosions taking place. Well, we looked at 2 small examples. We will deliberate on these during the course of our lectures, but we also find it is not only these accidental things which cause an explosion, but very often we find explosions do occur in nature. Like for instance, we have a lightning, that means you have these clouds which go at high velocities, accumulate charge, and when they have a high charge on them or a high voltage gets built up, what happens is you have this high voltage which gets earthed, and you have an electrical discharge. This electrical discharge again creates havoc, and not only that, you have lightning associated with thunder. That means there is a noise component to the naturally occurring explosions. It is not only lightning which causes the explosion in nature. You have these asteroids, comets which enter the atmosphere, and they also cause an explosion. Recently we had one in Siberia, and not only these two, you have stars which explode, you say nova, supernova explosions. Maybe these are the things which occur in nature and which we should also concern ourselves about. In addition to accidental explosions occurring in nature, of late we find there are some antisocial elements who intentionally promote explosions. What they do is they take these energetic materials and explode them in crowded places and cause grievous harm to people around them. What we say is improvised explosive devices is what they use. Maybe we should find out how they do, and we must find out how to prevent such explosions taking place. Therefore, I would like to say, well, explosions occur in nature, they are sometimes caused intentionally, but very often, most often they occur accidentally. And as engineers, since we handle substances which are energetic, it is necessary to sort of design our chemical plants, our plants in practice, such that we do not have the disruptive explosions taking place. Even though so far I have been telling explosions are disruptive, and that is how we have been connecting ourselves with the word explosions, we do find explosions could also be very constructive. What do you mean by a constructive explosion? I would hazard to tell you that maybe we would not have reached the present state of our development or civilization had it not been for explosions. Maybe I would like to say, yes, we need explosions to make tunnels, we need explosions to make canals, we need explosions to be able to blast rocks with which we make buildings, we need these materials of construction, and therefore, yes, there are constructive uses. Why? We would also need, you can use explosions for having microsurgeries. Why? Not only microsurgeries, maybe for injecting some medicines into the body, where I can use explosives. Why? Even the safety devices, we can use it for explosive forming of materials, maybe for fabrication, explosive forming, and the list is endless. The constructive uses are particularly large, and we shall look at some of these also during the course of this particular lectures. Having said that, let us go back and see what an explosion really means, and we will try to define what an explosion is in the particular talk today, and then maybe as time progresses, we will learn more about explosions, about the blast wave which is generated from explosions. Maybe we will look at the energy released from substances during chemical reactions, rate of energy release. We will look at the thermal theory of explosions. We will look at gaseous, maybe liquid explosives. We will look at explosives which come from ordinary foodstuff like dust, wheat, sugar and all that. Maybe we call it as dust explosions. We will take a look at physical explosions and so on, and therefore, broadly I can say the explosions can be categorized into 8 categories, and these 8 categories we will study during the course of these particular talks. Once we are very clear about these different types of explosions, we will look at the destructive effects, how to model the yield or how an explosion occurs and how the damage occurs, and then we will look at the risk analysis. In risk analysis, we will particularly look at how to calculate the probability of an explosion taking place and also the detrimental effects of the explosion. Having said that, something which I wanted to introduce at this point in time is, we said about the gas leaking and diffusing in a kitchen or in some open environment, and therefore, we would also like to take a look at atmospheric dispersion. Before looking at the quantitative effects of cataloging damages. This will be the overall overview of the course, and therefore, with this background of what this course is about, let us try to define what really is meant by the word explosions. When we look at the genesis of the word explosions, It comes from the Greek word explodere. In the olden times, especially in the then advanced countries like Greece, we had these operas in which the performers used to come and give a lot of talk. They used to keep on talking about different aspects, and sometimes these people used to be so much carried away that they kept on talking for hours together. This sort of irritated the audience, and the only way to chase out these people is by all the people clapping together. And this loud clapping got so loud that the performer was forced to leave the hall. That means, by the word explodere, what is meant is chasing out the people or driving out by a loud noise. And therefore, since an explosion is associated with a loud bang and disruption of things, the genesis of the word comes from the Greek word explodere. That means making a loud noise, such as by clapping and chasing out the concerned people or things, whatever it is. Therefore, we would like to first know, what do we mean by the word loud bang? That means, all what we are saying is an explosion should be capable of being heard. When I say being heard, means I have a loud noise. What is it which causes a loud noise? What is it which causes a disruption? And this is what I would like to dwell on today. Having said that, let us try to understand a little bit more. We are talking about a loud bang from an explosion. Therefore, let me go forward and try to build up a case for under what conditions can I hear a loud bang and disruption of things from the place they have been in. Therefore, to do that, let me start with a simple example. I brought with me a small flute over here, and what I do is I take this flute and blow into it. It makes a noise, it makes some sound. How does this sound wave propagate from this flute? Well, I create some disturbances, let us say at the tip over here. I create some disturbances. It is these disturbances which propagate and reach an observer over here, and this is what you hear as a noise or as a music. Now, how does this disturbance propagate? Well, you say it propagates through sound waves. When we say sound waves, what do we mean by a wave? A wave could be mechanical, a wave could be electromagnetic. Like for instance, you go to the beach, you go to the ocean, you find the waves coming over here. Maybe during earthquakes, you have the earth in the earth, which we call as seismic waves. Well, we talk of sound waves. What is the characteristics of these sound waves? What happens is, maybe when I create some disturbances, I create some compression, let us say compression over here, followed by rarefaction, that means I expand the gases, followed by compression, followed by expansion over here. Therefore, I have a series of compression followed by rarefaction, followed by compression, followed by rarefaction over here, and it is the front of this wave which comes and gives the message to us saying, well, this is what I hear. When I say this, when I say a wave, it is a progression of disturbances, but mind you, the matter from here does not really travel and reach me over here. It is only the matter at each particular point vibrates over here, either as a rarefaction or a compression, and it is progressively sort of transmitted to the adjacent layers, and I have the wave. Therefore, the wave does not have any mass as such. Even though it is able to carry the information to you, it does not have any mass, even though, let us say, the energy from here is reaching you over here. Therefore, let us say these are the mechanical waves. We could have electromagnetic waves, but an electromagnetic waves can travel through vacuum compared to a sound wave which requires a medium. Why does it require a medium? Well, I need the progression of these progressive movement of these disturbances. From here the particle transfers it to the next, to the next, to the next, and so on. Whereas in vacuum, I would not have this possible, therefore, a sound wave or any of these mechanical waves cannot travel through vacuum. But when we talk of electromagnetic waves, it can travel through vacuum, and the reason being, well, an electrical disturbance creates an oscillatory electrical disturbance, creates a mechanical disturbance, creates a magnetic disturbance, sort of an electrical disturbance, oscillatory, creates a magnetic disturbance, and this oscillatory magnetic disturbance again creates an electrical disturbance, oscillatory. This oscillatory electrical disturbance again creates a magnetic disturbance, and so on, and that is how an electromagnetic disturbance propagates through vacuum. We are not interested in these electromagnetic waves, we are more interested in sound waves, and we say, well, the progression of disturbances through a medium is by compression and rarefaction. Now, I was just telling you that the sound waves propagate through a series of compression and rarefaction, and therefore, if I were to idealize it and tell you, well, it propagates through a series of compression and rarefaction as it is possible to say, well, I have disturbances in pressure, which I denote as disturbances in pressure P prime. The ambient pressure is a pressure P naught, that is 1 atmosphere, or let us say 10 to the power 5 Pascal or 100 kilopascal is the ambient pressure at sea level. Well, over and above this, I have a small oscillating component, and it is this oscillating component or the disturbance which propagates. I can represent this. I can therefore say P prime at any instant. This is the ambient value of pressure P naught, over it I have the maximum amplitude is equal to P hat. Therefore, I can write P prime is equal to P naught P hat into I have sine theta, which tells me the shape of the sine wave. Well, I know that the phase here and the phase here is the same. Therefore, the wavelength is given by lambda, that is between points having the same phase over here, and therefore, if I were to put this is the direction of my propagation x, I can write this as equal to p hat into sine of 2 pi by lambda into x, because it is at the same phase 2 pi corresponding to lambda at any distance x. If I am interested in p prime, well, I have p prime is equal to p hat into sine of 2 pi by lambda x. Well, this gives me the type of compression and rarefaction which I can describe by p hat is equal to p prime is equal to p hat into sine 2 pi by lambda x. And now, but I said that the wave is travelling, disturbance is travelling, and this disturbance is travelling at the speed of sound. If the speed of sound is, let us say, a0, let us say now the wave is travelling at the speed a0, how do I represent it now? Now, I have to take into account the wave which is travelling. Let us put this together on this part of the board. This is now x, this is equal to the disturbance p. Initially we said, well, this is the compression and rarefaction over here. Now, this is equal to p hat over here, the maximum amplitude. What happens? The wave is travelling at the speed a0, therefore, at time t, maybe over a time t starts at 0, therefore, at time t, well, the distances travelled would have been over here, and therefore, now the wave progressively shifts over here, it comes over here, it comes over here, it reaches over here. This is the amplitude or the waveform at a time t, wherein this distance is equal to a0 into t, because at over a time t it travels this particular distance, and therefore, the equation for my wave, that means at any point over here for this x is going to be p prime is equal to p hat, where p hat is the maximum amplitude into sine of 2 pi by lambda into x minus at, right. Therefore, it is this wave which reaches me, and supposing I am somewhere over here, I hear these disturbances and I hear it as sound, as simple as that. Now, what is this velocity? We say it is the sound velocity a, or let us say a0 as I have been telling, and a0 is the sound velocity which all of us know under ambient conditions it is around 330 meters per second. Maybe in gases having low molecular mass the sound speed is higher, maybe in a metal the sound speed is higher, maybe in water it is also higher of the order of almost 900 to 1000 meters per second. Therefore, how do I get this expression? How do I find out how an expression for sound speed? Therefore, again I tell myself, well, this is the way the disturbances propagate, and now if I have a pipe or some area cross section, maybe I have a pipe of cross section, let us say A, and in this pipe let us say a sound wave travels at the speed A0. Now, the medium ahead of this is at condition, let us say P, it is at condition density is rho, pressure is P, density is rho, the temperature is T. And what happens? When the sound propagates into this medium, it changes the pressure slightly. There is some disturbance P prime at any point, it could be positive or negative. Maybe I have rho plus d rho, the density changes when the pressure changes, the density also changes, well, the temperature should also change slightly. And therefore, I tell myself, well, the effect of the propagation of sound at a velocity A0 is to change the properties of the medium from P to P plus dP, rho to rho plus d rho, T to T plus dt over here. Now, I want to write an expression, I want to calculate how the sound speed changes with pressure, temperature and density, and to be able to do that, I write the momentum equation, I write the continuity equation. Let us see what the continuity equation should be. Well, I have the wave which is travelling, and to write an equation when the wave is travelling is difficult. Therefore, I try to write an equation with the plane in the frame of reference of the wave itself. Rather, I sit on the wave and watch the fun. In other words, in the frame of reference of the wave itself, that means now I keep the wave stationary, and once I say I am sitting on the wave, that is with reference to the wave I am writing the equations. Well, the medium at pressure P, density rho, temperature T travels towards the wave at the speed A0. Mind you, here it was not, the medium was stationary, it was not moving. Now, with the wave stationary, well, the medium moves towards the wave at A0. Well, over here I have A0 plus dV over here, because I get a small velocity over disturbance over here, dV over here. The pressure now becomes P plus dP as earlier, the density is rho plus d rho over here, the temperature is T plus dt over here. Now, if I have to write the continuity equation, and continuity equation is very easily written in the frame of reference of the wave, because it is now stationary and the medium is moving. Therefore, what is it I find? If the cross sectional area of this particular pipe is A, then the mass which is moving towards this is A into A0 into rho 0 is the mass which is moving towards this, and which is moving away from the wave is equal to A into A0 plus dV into I have the density which is now rho plus d rho over here. Now, I find, well, A and A gets cancelled, and therefore, now I have A0 rho 0 or A0 into, I just use the word rho, not the rho 0 over here, A0 into rho is equal to, I expand this, I get A0 rho plus dV rho plus I have A0 rho plus dV rho plus A0 into d rho plus I also have the last term, namely dV into d rho. But if the disturbances associated with a sound wave are very small, well, dV is small, d rho is small, I can neglect this second order effect, and therefore, if I write this, if I look at this equation, A0 rho get cancelled, and I get dV rho is equal to minus A0 into d rho, or rather I get dV by d rho is equal to minus A0 by rho. This is from the continuity equation for a wave propagating. Now, I am interested in calculating the value of A0. Well, I do not know the velocity changes, and this maybe I would now like to take a look at the momentum equation. And what is momentum equation? We use the Newton's second law, rate of change of momentum is equal to the impressed force, and what is the impressed force dP into the area, and what is the rate of change of momentum? You have a mass, that is A, mass flow rate A, into the value A0 into the value is the mass flow rate, the change of velocity is dV, rate of change of momentum, is equal to the impressed force is equal to pressure into area minus, because the pressure acts opposite over here, therefore, I get is equal to A, that is the area of the pipe is A over here, A0 rho into dV is equal to A into dP over here, rather A and A gets cancelled, and I get dV by dP is equal to minus of dV by dP is equal to minus 1 over A0 into rho over here. This is from the momentum equation. I will put the continuity equation and the momentum equation together, and now if I take the inverse of this, I get dP by dV is equal to minus A0 rho, and I multiply by this, I get dP by d rho is equal to minus A0 rho, because I have dP by dV, I multiply by this, I get into minus of A0 by rho, or rather I get dP by d rho minus and minus becomes positive, and I get dP by d rho is equal to A0 square. Therefore, we find that the sound velocity can be given by dP by d rho is equal to A0 square. Of course, this implicitly assumes that the amplitudes of the wave motion, including p hat, p prime, are very small, such that I can neglect the second order effects over here. Now, when I look at this particular expression dP by d rho is equal to A0 square, I want to still be able to relate, I have still not been able to relate it to the properties of the medium, and now I tell myself, well, the amplitudes of the oscillations or the disturbances are so small that it could be reversible. What do we mean? Well, the value of p prime, the value of t prime, or dP, dt, and let us say d rho, which I call as rho prime, that is dP is p prime, dt is t prime, d rho is rho prime, are so small that it could go either way. That means it is somewhat reversible, and medium like air is something like an insulator, and when it is an insulator there is no heat transfer. Therefore, I can tell myself, well, the perturbations in pressure, density and temperature are so small that it could be reversible. Well, not only reversible, air is an insulator, and therefore, there is no heat transfer. Therefore, the process of sound propagation, we say, is both reversible as well as adiabatic. That means, it is isentropic, and therefore, I can say, well, dP by d rho is equal to A square. It would be for an isentropic process of sound propagating, and for an isentropic process, well, I can write P by rho to the power gamma is a constant, and therefore, let us try to change it again. P by rho to the power gamma constant is for an isentropic process, and therefore, I can write this as ln P minus gamma ln rho, taking ln on both sides, is equal to ln C. I differentiate this, I get dP by P minus gamma d rho by rho is equal to 0, constant is equal to 0, I differentiate it, and therefore, I get dP by d rho is equal to gamma p by rho. Therefore, for the particular case, maybe when I talk of small amplitude waves and sound waves are of small amplitude, I can write the sound speed A0 square is equal to dP by d rho, which is equal to gamma p by rho, and therefore, I have the expression for sound speed A0 square of the sound speed is equal to gamma p by rho. That means, I am able to relate the sound speed to the pressure in the medium, to the pressure to the density in the medium, and we know for medium like air, which can be assumed to be an ideal gas or a perfect gas. Well, a perfect gas is one in which the specific heats are also constant. Well, I can write P is equal to rho RT, or rather I get the value A0 square is equal to gamma RT, or rather the value of sound speed is equal to under root gamma r t. Therefore, I have been able to relate the sound speed to the temperature of the medium. Also we can tell, well, it is equal to the pressure, it is equal to the ratio of the pressure to the density, which is the square of the sound speed. Having said that, well, we tell ourselves, if I were to calculate, R is the specific gas constant, the units are R is equal to joule per kilogram Kelvin, T is the temperature. The value of sound speed at a temperature of around let us say 300 Kelvin, gamma for air is 1.4, it works out to be something like 330 meters per second. Well, therefore, we say, well, the sound speed depends on the temperature, it also depends on the pressure and rho, and for an ideal gas I relate it over there. But let us take a look at this propagation again. Well, the sound wave is propagating at a speed A0, and whenever you have pressure disturbances, I also have temperature disturbances. How do I get the magnitude of the temperature disturbances from the pressure disturbances is a question. Let us try to put that together before I am able to relate the sound, why in some cases I have a loud bang, in some cases I have this music from the flute as it were. Well, I now plot, well, this is my way, the propagation of my disturbances. I just take one wavelength, this is the value of P prime, this is the value of P hat, this is the value of the pressure of the medium, this is how it is propagating in the x direction. Associated with the pressure disturbances, I also get associated with the temperature disturbance. And how do I get the magnitude of the temperature disturbance? Well, I again say, well, the propagation of the wave is isentropic, therefore, I write P by rho to the power gamma is a constant. I also know from gas equation P by rho T is a constant. Well, this equation now I can write it as equal to P to the power 1 over gamma divided by rho is a constant, new constant, let us say C1. I use this equation along with this equation, and now see, I am interested in getting rid of the density, because I want to find out what is the magnitude of the temperature oscillation. Therefore, I divide one by the other, and what is it I get? I get P to the power over here 1 over gamma, I divide this by this, I get 1 minus 1 over gamma, and rho and rho gets cancelled because I am dividing this, rho comes on the top, divided by T, P by T divided by P to the power 1 over gamma by rho gets cancelled, is equal to a constant, or rather I get P to the power gamma minus 1 divided by gamma by T is a constant. Now, again I take the logarithmic differentiation, I get gamma minus 1 by gamma into ln P minus ln T is equal to ln C. I differentiate this and I get gamma minus 1 by gamma into dP by P minus dt by T is equal to 0, the right hand side being a constant, the differential, or rather I get dt is equal to the value of gamma minus 1 by gamma into dP is the small pressure disturbance P prime by P into I get the value of T over here. Therefore, we are able to find out that whenever there is a pressure fluctuation, well, I get a temperature fluctuation T prime is equal to dt, and therefore, I get a temperature fluctuation also over here. But mind you, whatever we did for very small amplitude waves such as sound waves, and which propagate isentropically. Now, I tell myself, well, I know a little bit about propagation of sound in a medium, which we just reviewed over here. Now, I want to find out, supposing by chance the amplitude of P prime or P hat is large, what could happen? Let me start with an example. Instead of, let us say, blowing in the flute to make a particular sound over here, I take a balloon, let us say, and into this balloon, instead of blowing constantly into this flute, I blow air into this balloon. I keep on blowing air into this balloon. That means what is it I am doing? I am increasing the potential energy of air into the balloon. I am pressurizing the air over here. The temperature may still be the ambient, but the pressure is higher, it has some potential energy. And so on, I keep on blowing, and when I blow, when I make this balloon sufficiently large and the fabric of the balloon is unable to contain the air, what is going to happen? Well, it is just going to burst, as it were. You know, this fabric is strong, it's holding the pressure, but if I keep on blowing, it's just going to burst. I am going to hear a sound over here, and this sound is what appears as a thud or a bang. Now, why should this happen? Let's try to understand a little bit more from this particular equation. You know what happens in this case, for a sound wave, the amplitude of pressure is small. Maybe if I can contain the energy which is released at the source, like the flute over here, you know what did I do? I take the I deliver some energy over here, which is propagating as a sound wave. Instead of that, I have a large amount of volume here, or a large amount of energy here, which liberates energy all of a sudden. Then what is going to happen? Let's try to see what could happen over here. You know, in other words, previously I have a sound wave, I have P prime over here, the ambient pressure is P, I have compression and rarefaction over here. Now, what is it I have done? Instead of the small amount of energy, I give a larger amount of energy. Therefore, since the larger amount of energy is given, the amplitude, that is the P hat of my wave, grows, and this is what it is going to look at when I have a larger amount of energy being released over here. Sort of it is, I have a larger amplitude over here, and therefore, now what is going to happen? I have a larger amplitude, and therefore, if I were to look at my temperature disturbance, previously let us say I plot the temperature disturbance, may be associated with a sound wave. Well, this is the type of temperature disturbance what I have. And now, when my amplitude is higher, well, the temperature disturbance is also going to be higher, somewhere over here shown by the red line over here. And now, what is it I find? Well, this is my T prime over here, above the base T over here. And now, the crest of the wave, when the amplitude is large, has a higher value of temperature equal to T plus T prime. Here, the temperature is still the ambient value T. Here, the temperature is going to be T minus T prime. And what did we find? We found that the value, that means as the pressure is higher, my temperature fluctuation is higher, and also I found, we had just derived this expression, namely the sound speed is proportional to the temperature, and therefore, what is it I find? I find that the wave here moves at a higher value of sound speed compared to the value of sound speed over here. If it is A0 here, it is going to be A0 plus dA0 over here. Because the temperature is higher, it moves faster. It is going to move slower over here. It is going to be A0 minus dA over here, dA0 over here. And therefore, what is the effect? Let us try to replot it such that we are very sure about what is happening. We therefore have P prime, we have x over here. Well, I have a larger amplitude in pressure over here, and therefore, I find that the speed over here is equal to A0 plus dA0, the speed here is equal to A0, the speed here is equal to A0 minus dA0. Let us make sure that we make these arrows corresponding to the speed little bit higher over here. This is normal over here, this is smaller over here, and therefore, after a small time when the wave has come over here, what is going to happen? This point moves larger, this point moves just A0 over here, and therefore, the waveform looks something like this, it gets little distorted. Well, this fellow does not go very far, and therefore, it comes over here, it comes over here, it comes over here, and then it comes. What has happened? The wave has got somewhat steepened, it is no longer symmetric, but this is steeper, and as it progresses further, what is going to happen? It is going to become more and more steep, maybe it is going to become like this, it is going to become even steeper, something like this over here. And ultimately what is going to happen? This is going to become like this, and therefore, it is going to become almost a plane, that means it goes like this, it comes like this, it becomes steep like this, and therefore, instead of having a smooth wave front in which I have a smooth compression followed by a smooth expansion, I have all of a sudden the wave becomes steep like this. Well, you could tell, well, the wave could also become something like this, because this moves faster. But at a particular point, I cannot get 2 or 3 different values, and therefore, the maximum what will happen is it becomes steep like this, and therefore, when the initial amplitude of the wave is large, the wave steepens into something like suddenly it becomes a spike like this, and this is what we call as a shock wave. What is the attribute to the shock wave? Well, it is a steep fronted wave across which there is a sudden change in property. Mind you, here the change in property was gradual, here the change in property was gradual, whereas here what has happened? From here all of a sudden I go to this particular property over here, there is a sudden jump in property, and this sudden change in property, this wave in which I have a steep fronted wave, that is in which there is a sudden change in property, is what we call as a shock wave. Mind you, the velocity of this wave is at a higher speed, and therefore, it propagates at a speed higher than the sound speed, and therefore, we tell ourselves if the localized energy release is such that I can, instead of forming a sound wave, if I form a large amplitude wave, well, I could have something like a shock wave, and the attribute of a shock wave is, well, it propagates at supersonic speed higher than that, and moreover it is something like a front is very steep. Here I have P, all of a sudden it becomes P plus P prime over here, the P prime is also large, and this sudden change is what we experience as a loud bang. All of a sudden you have a high pressure and you characterize it as a loud bang. Now, there is another aspect to this. Not only does the pressure all of a sudden jump to a high value, but there are, now you have gradients here, the gradient in pressure, that means I have dP by dx, I have gradient in velocity dV by dx, that means along x I have dt by dx, which are very high, because all of a sudden there is a change, and now I have heat transfer is equal to minus k into dt by dx, heat generation within the wave, I have shear forces due to the velocity gradients, and therefore, what is going to happen? Because of these gradients, the magnitude, that means the jump conditions are going to decrease, and therefore, this wave as it propagates is going to decrease in amplitude. Rather, instead of having a wave which travels at the constant speed a0, I create a wave which travels at supersonic speed, and the speed will keep on decreasing with time. Not only does it decrease because of dissipation, but what is going to happen? I have a wave like this, here I have compression, here I have rarefaction. The rarefaction is traveling in a medium at high temperatures. This rarefaction is going to catch up with the front and decrease the amplitude of the front, and therefore, the strength of the wave is going to keep decreasing, and such a shock wave whose strength keeps on decreasing as it progresses forward is what we call as a blast wave. We will consider the details of the blast wave in the next class, but to summarize at this particular point, I would like to say the following. Well, whenever we talk in terms of sound speed, we talk in terms of, let us say, a disturbance propagating at a small velocity a0. Now, if the amplitude of the disturbances are large, such as I release some energy instantaneously at a point, I start with a large amplitude and it intensifies into a shock wave. Now, this shock wave, what happens? It keeps decaying as it progresses further, rather the velocity keeps decreasing, and this decaying shock wave is what we call as a blast wave. If I were to put it together in a graphical form, maybe in a form wherein I have the axis over here t, I show the time on this axis, I show the distance over here. Well, what is going to happen? Well, the acoustic wave travels at sound speed a0, this is the sound wave. Initially, I start with a strong shock, travels much faster, therefore, maybe this is my shock wave. The shock wave, therefore, this is my acoustic wave or a sound wave. This is what I call as a shock wave traveling at a high speed, but this shock wave decays with respect to time and this becomes my blast wave. Therefore, a blast wave is a decaying shock wave, the pressure continually decreases within this, and because of the changing pressure I have wind or blowing of air into this, and that is what we call a blast of air, and therefore, a blast wave is associated with air moving at high velocities, and therefore, what happens? A blast wave is a finite amplitude wave, all of a sudden it takes place, I hear a loud bang and the velocity behind it or the blast behind it disrupts the thing, and that is what causes an explosion. Therefore, an explosion is basically categorized by a sudden phenomenon, namely having a blast wave, and the blast wave has a pressure rise across it, it travels at supersonic speed, all of a sudden the incidents happen, that means there is a sudden overpressure, there is a wind effect behind it which is a blast effect, and this blast effect disrupts the thing. Therefore, to come back to the point where we got started is, well, an explosion is categorized or is should be capable of being heard, or rather we tell ourselves, if we were to summarize what little we got started with today, we tell ourselves, if I have an energy release in the medium which creates a small disturbance, like I am talking to you, my throat is sort of creating some disturbances, the compression and rarefaction from it reach you as a sound wave, well, I have something like an acoustic wave. If instead of creating these small disturbances, and these small disturbances we say are isentropic in nature, what I do is I create much larger disturbances, and to create larger disturbances I took the example of a balloon, maybe I put lot of potential energy into it and burst it, all of a sudden the energy gets released over here, and when this energy gets released I start having maybe large amplitude waves which form something like a steep fronted wave which travels at a speed greater than the sound speed over here, and this, if it is not supported by the continual energy release, what happens? It keeps decaying as it progresses because of the dissipative effects at the wave front, because of the because of the high gradient in velocity. It is no longer a gradual compression which we hear as nice music or nice sound, but it is sudden. I hear something like a thud, or as we keep telling ourselves, a very loud bang as it were. And in addition to the bang, because it is decaying, the pressure keeps changing. I have the wind effects, the blast wind effects, and at the zone of the explosion, these wind effects scatter or disrupt the things. Therefore, an explosion is associated with a loud bang and disruption of things from the place from the place of the explosion. Having understood this, what we should do is we should look at more at the characteristics of a blast wave, and in the next class what I do is I will take a look at what are the how to model this blast wave. We find, well, it is not that simple for the reason, let us put some features into it. Well, what is going to happen? A blast wave, if I were to write over here, what is created by a finite energy release is sort of non-linear. What do we mean by non-linear? You know, it is something which is not like sound, which can go either way, which is sort of organized. You have something sudden happening over here, there is dissipation of energy taking place, and as the blast wave is going, the strength is changing. Therefore, it is a highly non-linear phenomenon. And therefore, in the first part, what we do is, since the problem tends to be complicated, we will do a simple dimensional analysis to be able to have some idea of the blast wave, and then we will go into the different types of explosions. We will study what are the different types of intentional explosions, what are the different types of natural explosions, accidental explosions, and then we will come back to the problem of details of a blast wave and modeling of explosions. Well then, thank you, and